Assalamualaikum and good day. We are going to learn about angular momentum from chapter 11. Okay, let's look at the relationship between vector product and torque. We can calculate torque by taking the cross product between vector r and f, where r is the distance from axis of rotation O to the point P where we apply the force F. The directions of torque is perpendicular to the plane of R and F. If you still remember, we use right-hand rule to determine the direction of torque. For example, if we take the cross product between vector A and B, which is equals to C, what you do is you point your forefinger towards the directions of A and curl your finger towards the directions of B. Your thumb will show you the directions of the third vector, which is C, which is also the torque. The force creates a torque that tends to rotate the body counterclockwise about the z-axis, so the torque is positive. If the directions of F is clockwise about the z-axis, the torque is negative. Let's look at angular momentum of a particle. So consider a particle of mass m located at the vector position r and moving with linear velocity v as shown in the figure below. The angular momentum L is pointed in the z direction. The instantaneous angular momentum L of the particle relative to the origin O is defined as the cross product of the particle's instantaneous position vector r and its instantaneous linear momentum p, which can be written as L equals to the cross product r and p. The SI unit for angular momentum is kilogram meter square per second. Both magnitude and directions of L depend on the choice of origin, that is the locations of the axis of rotation. We also use right-hand rule to determine the directions of angular momentum L, where you point your forefinger towards the directions of R and you curl your hand towards the directions of linear momentum P. Your thumb will show you the directions of angular momentum L. Because P equals to mv, the magnitude of L can be written as L equals to mvr sine phi, where phi is the angle between R and P. Therefore, if R is parallel with P, or the angle is 0 or 180 degrees, L equals to 0. But if R is perpendicular to P, or the angle is 90 degrees, we have maximum angular momentum, which is mvr. How torque relate to angular momentum of a particle? Okay, in linear motion, the net force on a particle equals the time rate of change of its linear momentum, which can be written by F equals to dp over dt, which is taken from equation 9.3 from chapter 9. In rotational motion, the net torque acting on the particle equals the time rate of change of its angular momentum and can be written as torque equals to dL over dt. To show this, the net torque on the particle is written as the cross product of R and F, where F is dp over dt, and we differentiate equation 11.5 with respect to time using the rule given by equation 11.2. Okay, this is equation 11.5 where we take dL over dt, where L is R cross P. So from equation 11.2, the differentiations of the cross product is written as R cross dp over dt plus dr over dt cross P. Okay, and dr over dt cross p equals to 0 because v equals to dr over dt is parallel to p. So the angle between them is 0, so sine 0 is 0. And in this case, the order must be preserved. Means that if you take r cross p, you have to write r first and then p. You write r first and then p. So our equation now becomes dl over dt equals to r cross dp over dt, where dp over dt is f, r cross f is the torque, so the torque equals to dl over dt, which we can write as equation 11.19. Okay, the total torque equals to dl over dt. Okay, how angular momentum L of a particle is related to moment inertia I. Okay, we write L as the cross product of R and P, where P equals to mv, and the equation R cross P can be written as mvr sine phi, where phi is 90 degrees because R and V are perpendicular to each other. So sine 90 degrees is 1. So V is replaced with R omega. So we have mi Ri square omega. Okay, as shown in the figure, where R and V is perpendicular with each other. So if we want to find the total angular momentum, where angular momentum is taken from this equation, so we know that when we look at mi Ri square, that is actually the equation to calculate the moment inertia of the system, where the equation L can be written as I omega. Okay, how angular momentum L of a particle is related to angular acceleration alpha. Okay, L equals to I omega. So if we write dl over dt, so omega is written as d omega over dt, where d omega over dt is alpha, the angular acceleration. So from here, we can write the torque equals to dl over dt, and we can also write the torque equals to I alpha. Okay, angular momentum of a system of particles. The total angular momentum of a system of the particles about some points is defined as the vector sum of the angular momenta of the individual particles. Okay, can be written as L1 plus L2 plus L3 and so forth until you sum over all the n particles in the system. Okay, we also have conservations of angular momentum, okay, where the resultant external torque acting on the system is 0. So from the equation, we can write that torque equals to 0, where torque equals to dl per dt. If you differentiate a constant value, you will get 0. Therefore, we can conclude that L is a constant value. So from there, we can write that initial angular momentum equals to final angular momentums, and we can also write I initial omega initial equals to I final omega final. Therefore, we have list down all the conservations of law, where we have conservations of energy, we have conservations of linear momentum, and we have a conservations of angular momentum for an isolated system. Thank you.